Thank you, Rob, for the introduction. Good afternoon, everyone. I am very happy to give you evidence how useful ionizing radiation can be in our life, even though we very often don't realize that products which we use were treated or were elaborated with the use of ionizing radiation. And also we benefit of technologies using ionizing radiation. I think that I have a much easier task because we have already heard three presentations with fundamentals, which are very good introduction to the application of radiation processing. I am very happy that working in the Institute of Nuclear Chemistry and Technology more than 20 years and where we use many of this application of ionizing radiation, I am very happy that I could introduce you the most important of them. Radiation processing is a treatment of products, of material with ionizing radiation for beneficial purposes. And these applications deliver significant environmental, economical, and social benefits worldwide. You can see here different of application of ionizing radiation. I tried to select the most important of its uses in different fields of medicine, industry, agriculture. As you can see, I decided arbitrarily, of course, divide applications into 5 different groups. So we have agriculture, health, environment, cultural heritage, and others. The first area of ionizing irradiation applications is agriculture with the flag application food irradiation. This process can be used for different purposes. We know that controlled doses of ionizing radiation can kill parasites or microorganisms such as molds, yeast, and bacteria that cause food spoilage and food poisoning. Food irradiation can be used to prevent stored food from infestation with insects, but also can be used to prevent food which is traded regionally or internationally from infestation. Another purpose of food irradiation is protein inhibition. And food irradiation also can be used for can replace the use of some preservative and pesticides, and can be used everywhere when heat must be avoided. So, for example, for fresh and frozen products. And you can see that microorganisms vary in their resistance to irradiation. And then their relative resistance can be compared through use the D10 values. And these are those required to achieve 90% of reduction in number of microorganisms. Unfortunately, we observe decrease in the amount of food irradiated in the European Union countries every year since 2002. And the main reason for that is probably the industry concern that consumers would refuse to buy food which is labeled as irradiated. There are 24 facilities approved for food irradiation in 14 European Union countries, and top product which are irradiated are frozen frog legs, herb and spices, and poultry. As you have already learned several times, we have 3 different sources of ionizing radiation, and also for food irradiation, all of them can be used. So food products can be irradiated with gamma rays from radioactive cobalt-60 or cesium-137. Can be irradiated with X-rays generated from machine sources operated at a nominal energy up to 5 MeV, and can be also irradiated with electrons generated from machine sources operated at a nominal energy level up to 10 megaelectronvolts. I would like to show you that different dose ranges are applied for different food products, and also to reach different goals. For example, low doses can be applied for the sprouting inhibitions, disinfection, and delay of physiological processes, while medium doses are used for extension of shelf life, pathogenic microorganism elimination, improvement in technological properties of food, and finally how high doses are used for industrial sterilization, for example meat or prepared foods, which can be later used, for example, by the astronauts. Labels of food products which were irradiated should mention that product was irradiated, and very often this sign, which is called radura, is used for this purpose. There are also different standards and regulations concerning food irradiation, and here we have an example of a list of food products and food ingredients which are authorized for the irradiation in different European Union countries. It is important to say that international organizations, including World Health Organization, have stated that food treated by irradiation poses no particular toxicological, microbiological, or nutritional problem. One of the fastest growing market in food irradiation is a phytosanitary treatment. We know that global trade and mass tourism contribute to spread of invasive insects, and this leads to crops losses, spread of diseases. It also has negative impact on the environment, and altogether give damage to a level of billions of dollars. So different methods are used to mitigate the spread. These are chemical methods, for example, methyl bromide can be used here, heat is used, cold treatment, but increasingly also irradiation. And countries that have imported fresh commodities which were disinfected via radiation are the USA, Australia, New Zealand, Indonesia, and Vietnam. And you can see that this is a growing trend, and every year more and more commodities are treated with ionizing radiation for phytosanitary application. In this application, low doses are applied. US FDA approved irradiation doses up to 1,000 grays for preservation and disinfection of fresh fruits and vegetables. However, still researches are being carried out in order to reduce doses which are required. And one of the issues which is being currently developed very intensively is a generic treatment. This is a single treatment that controls a broad group of pests without adversely affecting the quality, a wide range of commodities. Why is it so important? Usually, quarantine treatment is developed for one product and one pest at a time. So sometimes years of research are needed to develop effective protocol, then to approve this protocol and finally adopt this protocol. And if we have such a generic treatment, which is dedicated for a broad group of pests, this can greatly shorten process of gaining approval, export approval, and also save time and resources. And in these tables, we have some examples of generic treatment protocols which were developed and approved for different group of pests. And here doses up to 400 grays were applied. Another application in agriculture area, which have already been mentioned, is insect control. We know that insects can be vectors of serious human diseases, and their population needs to be controlled. And for example, in different regions of world, mosquitoes are responsible for spread of Zika and dengue viruses. And to mitigate the spread, usually insecticides are used. However, there is a negative, there is a concern, increasing concerns about negative impact of the insecticides on human health and environment, as well as there is also evidence that some insects become resistant to insecticides because they are used too extensively. So here also ionising radiation can be a help, and a method which is called SIT, sterile insect technique, was developed. What is the process of irradiation? So large numbers of mosquitoes are raised in a lab. Then male mosquitoes pupa are separated from female pupa and sterilized. And after that, they are regularly released to the environment to mate with a white female. And in the result, eggs won't hatch and population decreases. In this application, very low doses, tens of grays, are used, and it needs to be underlined that is only sterilization, no genetic mutation are introduced. Another application in agriculture area is a degradation of polysaccharides to obtain a plant growth promoters. Here we have example of carrageenan plant growth promoter. This is a food supplement which is extracted from seaweed, red seaweeds, and then degraded through gamma irradiation. Irradiation with ionizing radiation can induce some bioactivities in the polysaccharides, like growth promotion of plant or antibacterial activity, and solution of such degraded carrageenan is foliar sprayed on the plant, and then is absorbed through leaf tissue. And in the result, stems are stronger and roots stronger, plant has more tears, and it's more resistant to typhoons, and in the results we have more rice production. We can see very easily what is the difference in the plantation of seed. Rice we treated with carrageenan and planted without use of carrageenan. Not only carrageenan, but also chitosan can be used. And here we have example of the positive impact of degraded chitosan on the root system of the plant. The condition of germination strongly support the proliferation of present bacteria. Therefore, a seed decontamination method that provides efficient inactivation of microbial pathogens, while maintaining germination capacity and quality of the seeds is in high demand. And here also electron beam irradiation can be used, but only low energy electron beam irradiation. Why low? Because pathogenic microorganisms are usually only on the outer layer of the seeds. And inside we have something what is the most important for germination, embryo, so we cannot use high energy electron beam to penetrate in the whole volume and to destroy the embryo because the seed would be unused later. So we use electron beam irradiation with energy up to 300 kilo electron volt to penetrate not deeper than 100 micrometers in the seed and to destroy only bacteria present on the outer surface. And here different solution in irradiation was applied. Two-site irradiation, such toroidal source, but also we developed in our institute such rotation under beam system, which was applied for experiments. Now we can move to next application area, which is health, and with the flag application, which is sterilization. What kind of product can be sterilized? These are pharmaceutical or cosmetic ingredients, for example, which cannot be sterilized with chemical methods. Also medical products, starting from surgical gloves, also wound care products, implants such as hip joints, blood collection tubes, and many more. Also some laboratory consumables are sterilized, for example, Petri dishes. And finally, transplants such as tissue grafts are also sterilized, and there are estimations that around 40 or even more, a little more, % of medical equipment is sterilized with using of ionizing radiation. What is important during medical sterilization? So the first important issue is minimum dose, which ensure sterility insurance level. What is for medical sterilization 10 to -6 and indicates a probability of one item being contaminated in 1 million. However, very important issue is also the maximum dose, because polymer materials which constitute different devices have different radius sensitivity. So we have to determine the maximum dose in order not to alter material properties, functional properties, and also quality of the product. And next, application in health area is also sterilization, but tissue grafts. Sterilization is an important step in preparation of biological material for transplantation. And here also radiation sterilization is increasingly used because this process has many advantages. Besides high effectiveness, also possibility of the thermolabile material sterilization, because this is cold process. We can ensure dose homogeneity and also lack of toxic residues, what is very important in case of materials which will be in contact of the body or body fluids. And finally, possibility of sterilization in barrier packaging to prevent recontamination of the material. And we have different examples of tissue grafts which are sterilized. This is crushed bones and amnion. And those recommended for tissue graft sterilization by the International Atomic Energy Agency is 25 kilograms. However, in Poland, tissue banks recommended those 35 kilograms, and this is based on the years of the investigation of the influence of ionizing radiation on different tissue compounds, mainly collagen, and also on the evidence that some viruses, for example, human immunodeficiency virus, are resistant to doses of 25 kilograms. Another application in health area is radiation synthesis of hydrogels. Hydrogels is a 3D structure which can absorb a large amount of water or body fluids, and can be synthesized with the use of ionizing radiation. And in the process of irradiation of aqueous polymer solutions, very reactive species which are called radicals are created, and these radicals fastly react with the polymer molecules, and polymer radicals are created after recombinates and creates covalent bonds and cross-linked. And in the result we obtain 3D net of hydrogel, which is very good material for wound dressing, because it creates and keeps optimal moist wound environment, and also is transparent, so what allow observation of the condition of the wound, but also protect wound against external contamination, but on the other hand is permeable for oxygen. And what is important here, ionizing radiation has dual effect, because except besides cross-linking, we also sterilize product. And finally, the last one application in health area is something what is under development currently in our institute in the frame of the European project RADOV. The idea here is to elaborate and optimize irradiation conditions for hen egg proteins fragmentation, in order to get bioactive peptides, which later will be used for the production of two different products. hydrogel wood dressing with antibacterial properties, and packaging film with antioxidant properties. And these products also will be elaborated with the use of ionising radiation. And now we can move to the environmental area, and with the first application, which was developed in our institute, flue gas treatment. Use of coal in electric power plants and industry generates several environmental problems due to release of toxic gases, SO2 and NOx, which later contribute into acid rain production, which have very negative impact on the environment. And there are no methods which allow for removal of both these pollutants simultaneously, but we can use electron beam irradiation to remove both of them. And also in this technology, we obtain a byproduct, which is a mixture of ammonium sulfate and ammonium nitrate, which can be used as a fertilizer as such, or can be mixed with other components to produce commercial agriculture fertilizer. The first unit was constructed in the laboratory, and it was able to treat 400 cubic meters per hour, and was equipped in one accelerator with energy 2 MeV and power 20 kilowatts. Then this installation was scaled up, and in electric power plant near Warsaw, a bigger installation which was able to treat 20,000 cubic meters per hour, and equipped with 2 accelerators with energy of 700 kiloelectronvolts and power 50 kilowatts. And finally, the industrial installation was constructed in this place. This is an electric power plant in north of Poland. And this installation was a big installation equipped with 4 accelerators, each one with energy 700 kiloelectronvolts, and was able to treat 270,000 cubic meter per hour. And what is the level of the pollutants removal? So dose of 9.5 kilograms was sufficient. Excuse me. Was sufficient to treat both of them. And after optimization of the technology, we reached the level of the SO2 removal at 98% and above 80% of NOx removal. Wastewater also can be treated with application of electron beam accelerator, and different chemical substances can be degraded by the ionizing radiation. For example, chemical pesticides, herbicides and fungicides, which are present in agriculture wastewater, but also organic dyes, drugs and pharmaceutical residues. Also, petrochemical wastewater can be treated, and as we have already known, microorganisms can be inactivated. And here in fundamentals also is rely on water radiolysis, in which we produce radicals which are able to break down chemical bonds in different chemical substances, leading to their degradation. I will present examples of degradation of each of these substances during dedicated lecture on environmental application during the workshop in Reims. I can present the application of the wastewater treatment on the example of a pilot plant which was constructed in Daegu Industrial Dyeing Complex in South Korea. This is a rather big complex, including around 100 dyeing factories with high consumption of water, but also high production of wastewater. This wastewater is intensively colored and includes, except organic dyes, also other organic compounds like terephthalic acid or ethylene glycol. What is the main idea here? Wastewater was collected in the primary basin, then was pumped under the accelerator. However, we have to remember this is 1 MeV accelerator. Therefore, we need to have a thin layer under the beam to ensure the penetration and homogeneous dose in the whole volume. To produce such a layer, special injection nozzle was applied, and after irradiation, wastewater was directed to the biological treatment facility, which was combined with this pilot plant. Pilot plant was able to treat 1,000 cubic meter per day. And I would like to demonstrate how the solution look in practice. There were 3 identical accelerator with energy of 1 MeV and power 400 kilowatts. And this very interesting underbeam system, this is an injection nozzle 1.5 meter width, which forms this thin layer, which was later irradiated. And we can see that even low doses, 2 kilograms, results in the decrease of the biotreatment time, which is needed for further processing of the wastewater in the biological treatment plant. If wastewater is treated, why not sludges? We know that quantity of sewage sludge generated in Europe is constantly increasing. For example, in Poland, it is around 600,000 tons of dry mass only from municipal sewage sludges, and only less than 1/3 of this is used for recultivation in agriculture or for crop cultivation. These sludges contains different nutrients like sulfur, nitrogen, potassium, phosphorus, and also micronutrients, for example, copper. However, a significant part of organic matter which is present in sewage sludge comes from human and animal feces, and these excrements very often contain pathogenic bacteria, for example, Salmonella, but also parasites' eggs. So before we use it in agriculture, we need to disinfect them. And here also this action of ionizing radiation can be used when ionizing radiation react directly with the DNA, or firstly radicals are created and then they destroy the DNA. We see that in case of sludges, very low doses are effective in elimination of pathogenic bacteria, but also parasite eggs. And how the process looks in practice. The watered sludges came out of such nozzle to form a thin layer up to 100 micrometers, depending of the accelerator energy, on the stainless steel conveyor, and this layer is later transported under the beam and irradiated and finally collected in the container. Next application, which is under development currently in our institute, is ballast water treatment. What was the motivation here? So why ballast water is absolutely crucial for safe and efficient operation of modern shipping, providing balance and stability to unladen ships. It also may pose a serious ecological and health threat due to a variety of marine species which are carried from one place to another in ballast water. This include bacteria, microbes, aquatic organisms, eggs, cysts, and larvae of various species. And if such organisms enter new environment, can establish new population, then can become invasive, and this may lead to the extinction of native species. To prevent this danger, in 2004, the International Maritime Organization adopted the International Convention for Control and Management of Ships and Ballast Water Treatment, and this requires all ships in international traffic must comply with established discharge limits according to the D2 standard. And this D2 standard limits number of viable organisms of different sizes which are present in 1 cubic meter of ballast water, but also limits of number of so-called indicator bacteria which are present in 100 milliliters of ballast water. To meet these standards, different solutions are applied, for example, biocides. However, these substances have negative impact on the environment, but also UV treatment is widely used. However, this treatment is not always effective to all the marine species. So still new methods are being searched, and we, together with the Polish shipyard Remontowa, proposed a new approach with the application of electron beam radiation for the reduction of the biological contamination in ballast water. This is a complex technological line which was planned to be constructed in the floating dock. equipped not only with electron beam accelerator for ballast water disinfection, but also in different filters and reverse osmosis module for the removal of solid particles and different ions in order to get water which can be used for different purposes, for example, for ship washing, or also can be discharged to the port basin and complies with very strict integrated environmental permit. In this case, also layer of water need to be formed by special nozzles, and we use accelerator 1 with energy 1 MeV. We did number of experiments in a laboratory, but also using SMILE pilot plant, and we can conclude the dose of 2.5 kilograms is efficient in activation of the microorganisms and to comply with the D2 standards. I would like to also present this two very interesting photo of marine organism before irradiation and after irradiation, and here we can easily see what kind of destruction was done by the irradiation, which later leads to the organism death. Another application in environmental area also developed in our institute was ship diesel of gases treatment. The abatement of harmful pollutants such as SO2 and NOx has become an urgent issue in the marine industry since stringent regulation came into force. And during combustion of heavy oils used on cargo ships, a significant amount of highly concentrated SO2 and NOx is produced. And currently, unfortunately, there is no cost-effective and efficient technologies which are available to simultaneously remove sulfur and nitrogen oxide at such high concentration. Even though there are effective technologies which can remove each of these pollutants separately, like wet scrubbing for SO2 and selective catalytic reduction for NOx, these technologies have a number of drawbacks, for example, high installation cost, high maintaining cost, and also large space which is needed for placement of two installations and ammonium storage. Moreover, International Marine Organization also introduced some new limits in 2020, and according to the MARPOL Annex 6, the emission limit of 0.1% sulfur has been established in sulfur emission control area, and the emission limit of sulfur in global area was reduced from 3.5% to 0.5%. And similarly, concerning NOx emission, MARPOL Annex Tier 3 standard was applied in NOx emission control area in Europe, also in 2020, and it requires NOx emission must be below 2 grams NOx per kilowatt hour at marine engine speeds over 1,200 RPM. What is the composition of diesel engine exhaust gases? So concentration of NOx depends on the engine load and is in the range between 50 and 1,500 ppms. And concentration of SO2 is proportional to sulfur content in fuel and is in the range between 500 and 2000 ppms. So if we have a diesel engine with the power of 6 megawatts and 85% of engine load, and we take into account the strict regulation which were implemented in 2020, we can calculate that removal of NOx has to be higher than 79%. Taking into consideration the good solubility of SO2 and NOx and the availability of seawater, electron beam accelerator combined with the wet scrubber seems to be a good solution and might provide an answer to the reducing of SO2 and NOx emissions in marine industry. This process involves two steps. The first one is SO2 and NOx, mainly NO oxidation during irradiation process by the electron beam. And NOx is then oxidized to NO2 and higher oxides, and SO2 is oxidized to SO3 and higher oxides. And later, in the second stage of the process, SO3 and NO2 and higher oxides in the gas phase are absorbed into aqueous solution via wet scrubbing, and acetar forms. And in the result, cleaned off gases after electron beam wet scrubber treatment can be released into atmosphere. What are the results? So we can see that if we apply electron beam irradiation only alone, so then we don't have almost any effect. However, if we combine electron beam irradiation with wet scrubber, efficiency of the NOx removal increased to almost 50%. But please remember that this is still not enough because we need to reach 79% of removal. So what we can do? We can oxidize more NO to NO2 with addition of oxidants. So different oxidants were tested. Sodium chloride was the best. We also tested different concentration of sodium chloride. And with electron beam application combined with wet scrubber and also addition of sodium chloride, we reached efficiency of removal above 90% for the dose of 6.5 kilograms. So also in case SO2 for all hybrid processes, we have 100 removal of SO2 due to its excellent solubility in water. So in this in the result, we have technology which is able to remove both of these pollutants with high efficiency. And from environmental application, we can move to the cultural heritage area with the most common and most well-known application for the disinfection of cultural heritage objects, with these two spectacular application, irradiation of Ramses II mummy and also irradiation of baby mammoth mummy, which was carried out by the Nuclear Arts Center in Grenoble. This is a unique center where the conservation process can be carried out from very beginning to the end with the use of ionising radiation, gamma rays everywhere where is possible for or necessary for decontamination, microbiological decontamination or consolidation. We can see that different objects can be treated mainly with gamma radiation. Here we have example of a big painting which was placed in such a big box and irradiated with gamma rays in Brazil. But in institute, we also use electron beam irradiation for disinfection, mainly paper-based objects. Here we have example of 15th century altarings, but also notation of Polish famous composer Ignacy Paderewski and leather shoes from 15th century. This application maybe should be presented separately because this is not cultural heritage, but rather biosecurity application. When in 2001, mailed to recipients at Congress, the White House and the federal agencies were irradiated after spores of deadly bacterium anthrax were found in mail sent to the members of the news media and congressional leaders, and two installations equipped with electron beam accelerators in the USA were used for this purpose. And according to available data, more than 1 million containers of DC federal mail were irradiated from November 2001 till April 2008. And another application in this area is radiation consolidation. And the method uses vacuum impregnation with a liquid resin, followed with the polymerization under gamma irradiation. Or electron beam radiation, which is called radiation curing. And here we have example of 18th century parquet from Old City Hall in Grenoble, which was consolidated with using metal methacrylate as a consolidant, and it also was done in Grenoble. And here example of application of electron beam radiation in the area where this thin layer, which was on the outer layer of the terracotta army statue, was consolidated with use of electron beam irradiation just to consolidate the outer layer, not go deeper inside, because inside was a clay which was very sensitive to irradiation. And finally, cleaning, two different applications. The first one for the silver coins, on which this black layer of silver sulfide was formed, and with the use of electron beam induced plasma, this layer was removed. So the wet chemistry and abrasive didn't need to be used, and this minimized the strain of these fragile objects and side effects such as scratches and damages. And also, no hydrogels also can be used here as for the cleaning from the contaminants of different surfaces of cultural heritage objects. And finally, we can move to the last one category. All others where I place also polymers. So this is here we have an example of manufacturing process of heat shrinkable tubing, which consists of 3 steps. The first is extrusion, then irradiation, and finally expansion. And in, for example, polyethylene is extruded to form a tubular shape using extruder, then is cross-linked with high energy electron beam irradiation, and finally such cross-link polyethylene is softened in this heating zone and expanded in radial direction, and finally cooled to retain this expanded shape. From scientific point of view, we have polyethylene, which is a crystalline resin, and this resin consists of crystalline area and amorphous regions. And when it is electron beam irradiated, cross-linking reaction occurs in the amorphous areas. And then when such cross-linked polyethylene is heated at temperature above the melting point of crystalline area, the material becomes soft enough to be expanded, and when cooled, the expanded shape is retained by the growth of crystalline areas. And in opposite way, when expanded cross-linked polyethylene is reheated at a temperature above the crystalline melting point, the material is softened and shrinks to its original shapes to the cross-linked molecular chains of the amorphous area. And this is the well-known shape memory effect. And such materials have improved thermal, mechanical, and chemical properties. This is a process also solid state reaction free from chemicals, and this room temperature process, so energy is saved as well. Such materials can be used in different branches of the industry. For example, in the electronics, automotive, aerospace, and other industries for insulation or mechanical protection, like as a environmental sealing of electric wire terminals. Also as insulation protection of electronic parts of components, and corrosion protection of metal pipes, but also as shrinkable foil films. And the last one, not the last one, the next application in polymer area for manufacturing of tires. And after assembling various sheets of rubber and the other component materials, tires are molded using process which is called vulcanization. In this process, pressure and heat is added to form the tire. But before vulcanization process, the rubber is very soft and can be extremely easily deformed, causing issues with workability and material shifting out of the position, resulting in defects. So to solve this issue, electron beam processing is used on car splice and inner liners. And this is also a process which saves energy in case of application of electron beam irradiation. Carcass splice are contain cords which give strength to tire. And when this layer is thin, the cords can shift, resulting in defects when they perforate neighboring sheet layers. What is the solution? Usually make the rubber sheet thicker, but when we use electron beam to pre-cross link the rubber sheet before the vulcanization, we change the fluidity of the rubber, which decreasing, and this prevents material from becoming misaligned. In the results, we have thinner rubber sheets, and so material costs are lower, and also the tire is lighter and with higher quality. And the last one application in this area is gemstone coloration. This process involves irradiation of different gemstones. However, not each of them can be colorized with this with irradiation. And in the reaction of ionising radiation with crystalline lattice of gemstone, defects are created, and these defects later form color centers, which are responsible for the color change. And to conclude my presentation, I will sum it up with some outline of the future prospect for the radiation processing. Both technology, gamma and electron beam, are complementary in support of the development of different markets. Sterilization is most important application where gamma is used, while electron beam accelerators are preferred in environmental applications. There are well-grounded applications like medical sterilization and polymer processing, which are widely used. Even though food irradiation is considered a safe process by recognized international organizations, so it doesn't change regulators' attitude to liberalization of the conditions on which process may be applied, and this make this diffusion of the technology slow. However, on the other hand, we have continuous progress in amount of fresh fruits and vegetables, which are irradiated for phytosanitary purposes, which clearly demonstrates that these products are accepted by the customers. Also, different dynamics in the growth and the interest in different parts of the world is observed. For example, in Asia, this is a growing number of new facility. Asia seems to develop very intensively different applications, as well as also equipment are being developed. In North America and in Europe, still medical sterilization is the main application of the ionising radiation. And in different countries, locally, we have different applications. For example, in China, food irradiation is a big market. In Brazil, ionising radiation is widely used, for example, for cultural object disinfection. Electron beam accelerators have higher public acceptance, because here we have no use of radioactive substances, no storage, transport of disposal of such substances is not an issue. This is also a simple on-off system with high safety. So, however, there is also one main drawback. This is a penetration, limited penetration, what becomes a problem in case of high density products of pallets. And conversion with high-powered electron beam accelerators to the X-rays can soften this problem. However, all the time slow transition from gamma to electron beam X-rays are observed, because there are another problem with licensing of the process and so on. A problem in implementation of technology in environmental application, this is a need for a reliable high power mid-voltage shelf-shielded accelerators. And here maybe in future superconducting accelerators will be a solution. However, still further development is needed to make these accelerators more complex, more complex to be applied in line applications. And finally, also still low energy electron beam continues to grow in different applications, for example, in agriculture, but also in polymer treatment. And finally, thank you for your patience and thank you for your attention.